Welcome to Programming in Modern C++. We are in week 11 and we are going to discuss module 55. In the last module, we concluded discussions on several features of C++ which relate to classes and explained how these features enhance the object orientation, generic programming, readability, type safety and performance in C++ 11. In the current module, we in a way continue that discussion for several features of C++ 11 that apply to non-class types. We typically call them other types, and to templates, and the objective remains the same, is to enhance the OOP, generic programming, readability, performance, type safety and so on. In specific, we familiarize with very important features like enum class, fixed with integer, and most importantly the variadic templates. So, here is the outline, which as always will be available on the left panel. So, first we will discuss about non-types or non-class types, so to say, other types or non-class types. So, there are quite a few of them. So, the additions, the primary addition is enum class, which solves three significant problems that enum had in C++ 03. Then we have integer types to discuss, particularly the fixed with integer. Then we will say how unions have been generalized in C++ 11, and also the plain old data types have been somewhat generalized in C++ 11. And in particular, in between the sea of features that we will introduce here, particularly focus on learning enum class, fixed with integer and long very well. So, first talk about enum class. Enum, you know, is available in C++ 03. Actually, it was available in C as well. So, by enum we can define a set of tags which in C and C++ 03 take equivalent integer values, right, or we can provide specific tag values as well. Now, the problems that it deals it encounters is that it is implicitly convertible to integer even in C++ 03. So, even when you do not want such conversion to happen, you have no way to stop them. Also, the enum in C++ 03 export the enumerators to the surrounding scope, that is, it kind of makes them global. So, if you have an enumerated tag having certain name, then you cannot have another enum or another kind of global variable which has that name. So, that is a shortcoming. And finally, there is no underlying type specifiable in C++ 03 enum. It is always integer, it is always implemented in terms of integer. So, in C++ 11, this is enhanced to enums are enhanced to enum classes. The good old enum is also available, but we will prefer to use enum classes, which is also called the new enum, strong enum, scoped enum and so on, and they are strongly typed and scoped. So, let us start with examples. So, here is a C++ 03 enum. As you can say, I am defining an enum having different enumerator, 4 different enumerators, and I am defining a enum class in C++ 11. So, what is new is after the keyword enum and before the name of the enumeration, you write this keyword class, and rest of it is written in the same way. Right? Now, the moment you write it as a class, it kind of imposes a namespace onto the set of enumerated values. Right? So, there is another enum class here, and you can see that if you see the enum class color and enum class traffic light, you will see that I am using common enumeration of red, which in C++03 would not have been possible. Now, let us see what happens if you do try to define A, declare A with initialization 7. This is error in C++03 because you have only 4 enumerations. In color, if you want to do the same thing, you will also have an error, because if you want to do this, first of all, the first error that you get is because 7 is an integer and color is now a defined class, an enum class. So, there is no conversion available between them. Now, old ones like assigning red to A2 is possible, because alert can be converted to int, as you know, in C++03. Now, if you take alert : red specifically, then it is an error in C++03, because in C++03 the names were global. Now, we are writing it in a scoped manner. So, this is okay only in C++11. If I try to set blue, it is obviously an error because it is not in the scope, but if I say color : blue, then it is fine. But I cannot define a variable of type int and initialize with color : blue, because color : blue has a different type than int and there is no conversion. I can only have a variable of type color to be able to do this, right. I can only have this, right. So, that is the basic thing. So, let us look at these 3 aspects one by one. Let us talk about scope. So, here I have defined 4 enums in C++03 and they will have severe problems, because silver is common between them, gold is common between them, and so on. But if you look at semantically, then these are not synthetic examples. So, in terms of color, you will certainly consider bronze, silver, gold as color. In terms of Boolean, that is the coins, currency coins, you will certainly have silver and gold. In terms of metal, you will talk about silver, gold, platinum as metal. In terms of credit card, you will talk about silver, gold, platinum. In terms of memberships, you will talk about that. So, it is the same kind of tag name is applicable in multiple contexts, which is not expressible in C++03. In C++11, by using this enum class, you can easily do that. These names are all now scoped within the particular enum class. So, silver here is actually color : silver, and silver here is Boolean : silver. So, the names do not clash anymore. So, with this scoping, we can enhance the expressibility of enums to a significant extent. If we look at the underlying type, then we know that in C++03 the underlying type was always int. It is enum is converted to int, but now you can specify what is the underlying type. So, what you do is the syntax for that is, after the enum name and before the list starts, you put a colon and then write the underlying type name. So, this is kind of similar to the way you write derived classes, you can say. So, this is the underlying type, and when you do that, the enumerator definitions follow that underlying. For example, if I for status, if I have written std : uint 8t, which means it is an unsigned integer of 8 bits, is that I will use as my underlying type, then this becomes an error. But if you had not written this, if you had not specified this, then the underlying type by default is int, and therefore 9999 is a valid value in int, and this will be accepted. So, this gives a kind of strong typing to enums, and you cannot compare scoped enum values with ints. You cannot compare scoped enum objects of different types. You cannot I mean, it is not, int is not cannot be explicitly cast into enum or otherwise. You have to implicitly cast in that, you have to do that explicitly and so on. So, here are a couple of examples of here is an elevation and a voltage. Both of them could be low and high, and for example, if I try to define E with low, I will get an error because it is not scoped. I have to write it whether I have to specifically say that it is elevation : low. Similarly, voltage : high. I cannot compare E with voltage : high because E is of type elevation and voltage is of voltage : high is of type voltage. So, you can see that basic difference, that is kind of the notion that we have strong typing in terms of classes come in here with the convenience of having the tags of the enums. Finally, with these another big advantage that you get, you can now forward declare enums. So, if you try to just say that, well, I want to say that I have an enumeration, but I am not right now, I am not sure about the enumerators and I do not want to list them out. You cannot do that in C++03. So, if you just write enum this, then it will give you an error saying that the size is unknown, because unless you give the list, the compiler does not know the size. But if you write it like this, saying that the underlying type is such and such, then the compiler immediately understands that you are talking about, not talking about enum in C++03, but you are talking about an enum class, even though you have not written the keyword class. But from the syntax of the underlying type, the compiler figures out that you are talking about an enum class, and it will allow you to specify this without the enumerators being specified. Similar thing can be done here, and then it can be used in terms of passing to passing as function parameters and so on. Of course, before the actual execution, you will have to specify what the enumerations are, and only then the code can be generated. So, this gives enum class really a much stronger and much well typed behavior in C++03, C++11 compared to what you had in C++03, and you must start using them extensively. The next feature is about the types, integer types. Now, as you know that we have different integral types in C++03. There is unsigned char, there is char, there is short, there is int, there is long, and so on and so forth, right. Now, if I ask you what is the size of say int, or what is the size of char, or what is the size of long, you will say that it depends on the implementation, because the standard has not defined what the size will be, right. So, it depends on the compiler and the actual implementation which defines the size of every type in C++03, with the exception of unsigned char, which has been defined to be 1 byte, that is 8 bits in the standard. Otherwise, these sizes are unspecified. Only thing that the standard specify is there is an ordering between their size, that is unsigned char cannot be larger than the size of char, that cannot be larger than the size of short, and so on and so forth, right. In contrast, in C++11, you have a number of types which are either directly implemented or given as type defs, that is type alias, in this particular component called cstd int. So, you can see that it is actually being borrowed from the C standard library, because this also is a part of the C99 feature, right. So, you have things like say int nt. Let's just look at one and the rest will become. So, here by this what I mean one of these numbers, that is, it could be 8, it could be 16, it could be 32, it could be 64. So, for example, if n is 8, then the name of that type in the cstd int is int8 underscore t. So, this tells you that this is an integer type which is signed and must be of 8 bits specifically, so fixed one, right. So, the implementer has to give you kind of a way to do that. So, it has to be exactly, or this type will not be available. If it is if it is not available, then you will get a compilation error. So, you will know that you cannot do this on the particular implementation you are using. But if it is available, if it compiles, then you are guaranteed that you will have a 8-bit signed integer. Similar thing you have for unsigned integer as well, and the signed integer is represented in n bits with no padding bits, and signed it is represented also as 2's complement for negative values. You have two other such, one is called int fast. Int fast is implementer's judgment on what is the fastest signed type of size n that is available, right. So, the implementer will type def it appropriately, so to a particular type. It could be, for example, int fast 8t could be type def to char, because it is 1 bit and it could be the fastest. Similarly, there is a int list, it say what is the smallest integer type. I mean it maps to it type defs to the smallest integer type having at least n bits. Please note that between int n and int fast n or int list n, the difference is int n needs exactly n number of bits, whereas these two need at least n number of bits. So, even bigger size will also work. So, these are the fixed types. So, what is the difference between them? What is the difference between int t, int list t, int fast 8t and so on? So, suppose you have a compiler, some hypothetical machine which is a 36-bit system. Do not get shocked with that, because your PCs and servers are not the only computing systems that exist in the world. There are several other embedded systems and so on which has arbitrary number of bits available for them. So, suppose you have a 36-bit system where the char is 9 bits, short is 18 bits, double of that, and int is 36 bits and long is 72 bits. Now, in this, if you try to see what is int 8, it is, you will see that it does not exist, because it has to give you an integer type with exactly 8 bits, which does not exist. So, with this type, the code will not compile. So, which tells you clearly that 8 bits are not, 8-bit integers are not available. Whereas, the int list 8t will be a type def of char, because it is the smallest signed integer having at least 8 bits. So, char has 9 bits. So, it satisfies the at least part, and between 9, 18, 36, 72 it is the smallest. So, the list int list 8t will type def to char in this system, whereas int fast 8t could be anything, depends on what the implementer considers it the most appropriate type for the speed is concerned. Right? You also have in C++ 11 a new type called long for integer, which is meant for 64-bit integer. So, here is an example of a long variable being declared with a literal, but mind you that you cannot write long, or you cannot write short long, those things do not make any sense. Besides that, several extended precision, but the biggest take back for you from this should be that fixed width integer types are possible now in C++ 11, and in terms of 64-bit computation, you have the long as a new integral type for 64 bits. Moving on, union, as you know, is a collection of mixed types like in structure, but the fact that only one component can be available in a union at any point of time. So, this naturally creates a problem. Suppose if I define this as a union, I do not know which of these components is being used. Therefore, to construct the object of this union, which constructor should I use? Constructor of int, maybe, which is the POD default constructor, or the constructor of complex, or the constructor of string. So, therefore, C++ 03 does not allow any component of a union to be a user defined type having constructor, destructor, assignment and so on. This is simply not allowed. In C++11, this rule has been somewhat relaxed. So, it says that well, you can use such member variables in a union provided these rules are followed. That is, the member you are including does not have any virtual function or a reference or base class, and if it defines any of the constructor, copy or destructor, then the corresponding function in the union gets automatically deleted, right. You cannot, because you cannot then delete. I mean, if you have defined a constructor, then you cannot have a constructor for the union, right. So, this kind of may look little weird to you, but if we see an example, you can easily make out. So, this U1 has int and complex, so it is okay. In U2 you have int string, right. So, if you try to, this is an error, because the moment you have U2, then the string destructor will cause that U2's destructor is deleted. So, there is no destructor, so U2 cannot be defined. So, you will wonder as to why then have this. The basic point is, if you are making a discriminated union, that is, you are making an union where you use a enum class tag. We have seen this style before in C++03 also, and say 3 types, point, string and int, 3 types of variables, then you will be able to still do that. Only difference is you will have to now define your operators, like say if you have to give assignment to this, because assignment per se will not be given, it is because string has an assignment operator. So, you have to provide an assignment operator now, no default is to be provided, where you can specifically decide based on the components and decide on what needs to be done. Please go through this code, this should be pretty straightforward to understand, and you will know why this how this generalized union work. There is a some generalization of the plain old data types also, which are bitwise copyable by memcopy or initializable by memset, like if I had a struct without any constructor. Now, that is a plain old data type, because that is a bit pattern. In terms of C++03 also, these kind of classes or structs are also considered to be a plain old data type, because what it is actually doing is basically assigning a pattern to the data member, right. So, again the plain old data type extends a lot with 2 basic rules. One is any structure is a plain old data type provided all members and bases are plain old data type. Everything inside is plain old data type. So, that I can bit copy everything, bit initialize everything, and naturally there is no virtual function, no virtual base, no reference and no multiple access specifier. All access specification has to be the same. So, the crux of the thing is that it becomes in C++11 a data type becomes a plain old data type if it does not make a difference whether I have a constructor or I do not. In terms of the layout or in terms of the performance, if it does not make a difference, then it becomes a plain old data type. I am not going into the details of that, just the notions are important, because in terms of actual programming, I would not advise that you use these as plain old data types in general. These are meant more for the experienced library programmer, and you should restrict, but you should know that such kind of codes are expected. Now, let us move on to templates. So, there are varied extensions to templates. First, there is an external template, template alias, variadic template is the most important, local type arguments, right angle brackets and variable templates. Of these 2 are the most important ones. External template is simply, if you have a template, I have to instantiate it at multiple places, then naturally it is expanded at every instantiation phase, whereas those instantiations for the same template type parameter would be identical. So, it allows C++11 allows that you can use the instantiation of a template, but tell the compiler that don't instantiate it here, it will be instantiated somewhere else. So, in some other file it is instantiated and used. So, it is basically a performance issue for the compiler, not a great thing for really the programmer's semantics. Template alias is nothing but using a different name for a template with one or more of its parameter types already specified. There is a detailed discussion here, but what I want to really make you to note is consider this example. Suppose you have defined a class matrix as a template. Naturally, you will have 3 template parameters. One is the type of the element, and there are 2 non-template non-type parameters like int, line, number of lines and number of columns. Right? But specifically, you also want to deal with squares and vectors. What will happen in a square? The line and column must be same. What will happen in a vector? In the vector, the number of columns should be 1, right? It's a linear one. So, this is what you can do using the template alias. For example, take that matrix template, you are making both of them same and defining a new template with T and line and giving it a name square. This keyword use of this keyword using here allows you to do that. So, square now becomes an alias for this matrix template, where you can just provide the type and the line, and it will use the matrix template with the line and the column both being same as the line. Similar thing you can do for a vector as well. Right? So, that makes naturally the expression lot more readable, expressible and semantically clear. Now, what is a significant contribution of C++11 in terms of templates is what is known as Variadic template. What is a Variadic template? A Variadic template is one where there is variable number of type parameters, type non-type parameters. Right? So, why is that important? Because we have Variadic functions. The most well known Variadic function is printf, right, where we know that we have a one parameter, first parameter is must, which is format string, and then we just say ellipses dot 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 to mean that there could be any number of parameters, and that is a real sore for the type checking, because in the code you do not get to see what the type is. Corresponding the format definition like %d, %s with the actual parameter type is user's responsibility. So, printf is a really sore area. Using Variadic templates, you can do this, get rid of this by specifying the printf in a very type safe manner. What you do first is you write a template just for the write a template function just for the format string. So, you have the format string s, and you will have percentage or percentage. If you have if you do not have any of that, then naturally then it is not valid. Otherwise, you just print whatever text is given. What is there in the format string? There is %d, %s like that. There are certain character strings or %. So, here you take out those and anything in the character you print. So, that is how you deal the format. Now, you do what is the Variadic template. Here note carefully that I said that there has to be a first type T, and then there are dot 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 Variadic number of template parameters. Similarly, in the function I have given that first parameter is the string, the format string, second is a value which is t of type t, and then the rest of the parameters. Right. So, what I do is I taking this. So, Here I have say 3 parameters. Here what I am doing is I am taking out one, the first of them, and remaining 2 I keep as a separate pack. So, as if there is a pack of 3 parameters given, I take out the first one and leave the other 2 in the pack itself. So, the one that I take out, I simply do an std out. I do not care about what is the percentage d percentage s, because in C++ we know that how to print, how to stream is known from the type. So, I use that feature. And then I simply recur, and when I recur, I use the format string again as a first parameter here, and rest of whatever is remaining. And if I do that, then naturally it will keep on, you will call this function itself with one less parameter. Then again it will call this function itself with one less template parameter till it has only the format string left, in which case it will call this particular version. So, that is the typical way the recursion works, though you may not strictly call it a recursion. This is called variadic template. This is not strictly called a recursion, because in recursion you expect the same function to be called recursively, but here every time the function is changing, because every time the function has certain number of parameters, where a bunch of parameters are packed, and when it calls the next version, it actually has reduced one parameter from the pack, right. So, that is what the printf does. So, you can think of I mean, if you think about lambdas in C++, you will know that this basically is a kind of a functional programming at the compile time that we are doing, right. So, it's printf is just, so this is a very easy way, very short code, and if you actually look the printf code in C, it is a very huge one. It is a very short code, which is a very type safe way to print anything that you wanted to print in that way. In fact, it allows you to also print user defined types, provided you have overloaded the output streaming operator appropriately. Now, let us think about doing this to build an adder. Suppose I want to build an adder function to add arbitrary number of values, right. So, I define an adder function first for one value, single value. So, I say if it is a single value to add, it is that value itself. Otherwise, I use variadic template. What do I do? I say that I have two things. One is I have the type of the value being added, and the other is I have a pack of parameters. In the recursive or variadic call, I define adder with the first parameter from the pack. I call it first. It has to have the type T, right, and I leave the remaining function parameters within the pack, right. It will stay there. And then what do? I have the first value. So, what is the addition of the entire thing? Is the first value plus whatever is the addition of the remaining pack, which is a recursive call with the remaining function parameter pack. So, if I try to do this on adder 1, 2, 3, 8, 7, it will give me 21, and this is how it actually expands. So, what I have used here for demonstration, I have used a macro from GCC, online GDB compiler that you are using, so that you can try out. So, that will tell you for every variadic expansion what is it being expanded onto. So, what happens is when you first try to instantiate call this template. So, what will happen is first parameter is int, T is int, right. So, that goes there, and the remaining 2, 3, 8, 7 is packed into 4 ints, right. So, you have 1 plus the remaining has to be added. So, you go to the recurrence. As you go to the recurrence, now you are expanding on 2, 3, 8, 7. So, this was 1. So, this now becomes 2. The first one is gone, and what you are left with is just 2, 3, 8, 3 in the pack. So, you have 1 plus, 2 plus, 3 plus, 8 plus, goes on in this way. And when you hit this, you call t with int, which is basically the exit function call. All expands, computed, right. A beautiful way to actually write very compact, compile time, for any constant values is a compile time computed functional programming which is at hand. It can be used for example, this adder could be used for any type which has operator plus defined. Right. So, this variadic template is a very important feature. So, therefore, I have given 2 practice examples. One is a peculiar way of squaring and adding that you should try out, and another is a simple example to show that how can you write a variadic template to just count in an instantiation of the variadic template how many template parameters you have actually given, right. So, this will give you that count. Try this out at home. Some of the less important features of templates use include local types as template arguments. For example, in C++03 within a template function you cannot use a type that is local here. With C++11 you can use that. You can also use types which do not have a name, unnamed types. So, these are minor features which you have, which you may or may not use. There are other ways of doing that. But this is important that in terms of syntax, C++03 had a major difficulty in terms of nested template. So, this is a nested template. So, what I am saying is std list int. So, I have a list of integer and then have a vector of it. So, naturally this will be the syntax. Now, the problem is this one is a right shift. As you write 2 consecutive right angle bracket, then it actually represents right shift in C++03. So, C++03 gives you an error, and you have to write it, remember to write them with a gap, right, which is unnatural. In C++11 this problem has been solved. So, you can write them as consecutive symbols. But this certainly means that when you want to write specifically about shifting along with the template expansion, you will get into subsequent errors, and you will have to guard them by putting proper parentheses, which is a very rare case, but this is a big advantage. The last but not the least is an extension that is not in C++11, but in C++14, is that you have so far known templates are for classes, templates are for functions. So, you cannot have a variable as a template. So, if you want to have that, then you have to define a class, define it as static within that, and so on and so forth. But in C++11, you can simply have a variable as a template. So, here n is a simple variable. So, you say n is of type t. You can also specify a default value for that and use it simply in this way. This is something which was earlier restricted only to classes and functions, but in C++14 you can have variables also which are templatized. There is a bigger example below here which illustrates the same thing. It could be just a variable, or it could be a constant variable, and so on, but its instantiation will actually create that variable in your code. So, that brings us to the end of this module, where we have introduced several features of C++11 for non-class types and templates with examples. And I remind you again that it is very important that you learn the non-class type features like enum class and fixed width integer, and among templates the variadic templates will be very, very important to work with. Thank you very much for your attention. See you in the next week.